Hi, everyone. Welcome to the second session for this JChampions 2021 conference. My name is Josh Juno, and I'll be the moderator for this session. This second talk is entitled Introduction to Micronaut, and our speaker is a very well-known Graeme Rocher. Graeme is the creator of several popular open source projects, including Grails and Micronaut. Before we start, I do want to note that you can ask questions via the YouTube chat, and I'll make sure to make them available for Graeme at the end of the session. Okay, so without further ado, I'll go ahead and I'll hand it over to Graeme for the presentation. Thanks, Graeme.
Thanks a lot, Josh. Pleasure to be here in the inaugural JChampions conference. I'm privileged to be invited, and welcome to this talk on an introduction to Micronaut and GraalVM. As Josh mentioned, created a couple of relatively well-known Java frameworks in the ecosystem, in the open source ecosystem. Grails, which is significantly longer in the tooth, I guess you would say, having been created back in 2007. And more recently, Micronaut. I work as an architect at Oracle Labs, and I'm now Java champion and alumni, as I'm not working at Oracle. And I'm essentially leading Oracle's contributions to Micronaut. You can connect with me via social at those two links if you want to get in touch. So on the agenda today, we're going to look at the background that led to Micronaut. We'll do an introduction to Micronaut, introduction to what GraalVM is, combine them together in some demos and have a lot of fun, hopefully. So in terms of the background that led to Micronaut, 10 years ago, we were building very different very different architectures in terms of the way we built applications. Applications were typically deployed to a single Java virtual machine and via an application server, whether that be your Tomcats or your JBosses or your WebLogics or whatever it may be. And these containers have the opportunity to share resources amongst the different applications. And if you fast forward to today's workloads and how people are structuring applications, there's a lot more deployment of Java applications inside containers, using a container orchestration layer like Kubernetes to orchestrate the applications and manage them. You have a diverse range of applications in terms of things like your typical microservices, but also serverless functions and streaming applications, headless applications, and so on. So architecture has really changed fundamentally from what it was 10 years ago. So like I said, you have these two very different ways of developing, and existing tools and frameworks were built specifically with the traditional stack in mind, the servlet APIs, the shared single JVM, war deployment, and so forth. And they weren't really designed for an orchestrated approach where they're running within containers and so forth, deployment by Docker container registries. And in order to achieve those goals, traditional frameworks like over the years, like Jakarta, Spring, CDI, and so forth, made extensive use of techniques that are not great from memory consumption performance in a startup performance perspective. So things like the use of reflection, runtime bytecode generation, runtime generated proxies, dynamic class loading, and so forth. All of these kind of had adverse impacts on the memory consumption and start time of your application. And when you're trying to optimize an application to use less memory, it became evident when we were researching how we could improve the experience in Micronaut that the usage of reflection was a real sore point, and frameworks that were based on it was difficult to control the memory usage. But it's not all about performance and memory consumption. Productivity and developer productivity are seriously important aspects to developers as well. And so in general, the state today is that although things are not optimal, most people live with the scenario as it is because the productivity of by frameworks based on those approaches. So, in our research, when we started looking at building Micronaut, we wanted to reduce this coupling between the size of your code base and the start time and memory consumption, this kind of link between the two. In order to do that, we had to look at Java's problems for frameworks in terms of the key building blocks that a framework developer has to deal with. And myself, having been building frameworks which are the Java space for over 13 years now with Rails and Micronaut, could kind of understand the main issues that every framework developer faces, whether you're writing a Java application server or CDI or Spring or whatever. And many of these aspects are essentially common across all framework developers in terms of things like the annotation API in Java being fairly limited, in that it exposes the annotation on a particular element, whether that be a method or a class or whatever, but doesn't really deal with the notion of meta annotations or annotations and inheriting annotations from interfaces and so forth. So most frameworks have to kind of add that behavior afterwards. And the other issue is that the annotation API itself is based on reflective access. So you have to reflectively access a method to get its annotations, which means that it's kind of enforces you to use reflection. Reflection is, as I mentioned, a problem because it leads to uncontrolled memory consumption and the growth of reflective data caches. If you look at like a typical Java application, it might have, for example, Jackson, Spring, Hibernate, and each of those tools that builds their own reflective data cache, which can lead to serious inefficiencies in terms of memory consumption in larger applications. Another thing was like type erasure with generics being added afterwards, but developers still wanting to use generics in their applications to expose that this is a list of string or whatever. Each framework has to add extensive logic to intentionally retrieve those generics by reflection at runtime, which leads to, again, slow analysis of your classes at runtime. And then, certain other techniques which have become less and less common over the years, like class path scanning, where essentially a lot of frameworks would scan the class path of a Java application by doing a disk I/O to look for all the components that are annotated with a particular annotation. This could lead to like seriously slow startup. And but then again, in Java, it doesn't really provide a way out of the box to discover all the classes that are annotated with a controller or something like that. In addition, traditional stacks based on the servlet API and traditional stacks like Tomcat and so forth have extensive class loading hierarchies where you have, in order to support the ability to load and unload an application at runtime, because they have to support use cases like deploying a WAR file and then undeploying that WAR file and redeploying it at runtime without stopping the JVM. And this leads to very complicated class loading hierarchies in these containers that really add a lot of complexity and slowness in terms of dynamic class loading, which is like not really needed or necessary in a case where you're deploying to a container or as an embedded jar file, because it's just completely unnecessary. The redeployment is going to happen by the container orchestrator, for example. So I bang on about reflection a lot and why it's a problem, but it's fairly obvious. If you want to find out why it's a problem, you can go and look at the JDK. It was all open JDK now, it's on GitHub, and you will find that the source code for java.lang.class is there. And what happens is essentially the first time you access reflective data on a class, all of the reflective data for that class is initialized on first access. When I say all, there's literally all. So every field, method, constructor, etc. is initialized in one go. And for large class files, that can be serious amounts of memory being consumed. And the references for these methods and fields and constructors and so forth are stored in soft references, and soft references don't get garbage collected until the application is actually low on memory. So it's inefficient to load, and it's inefficient to store, and leads to what I regard as the uncontrolled memory usage problem, because you as a framework developer, or myself as a framework developer, cannot control the size of an end user's code base. Therefore, you cannot estimate or know how much memory is going to be used by the end user's application, because it's dependent on how many lines of code, how many methods, how many fields, which is a difficult catch-22. So with that in mind, we did a lot of research and into what we could do, and came up with something called Micronaut back in 2018, when it was born. And Micronaut is essentially a variety of things depending on your use case. So for a lot of people, Micronaut is a microservice and serverless focused framework. That's the name. But for other people, it's also a complete application framework for any type of application. So Micronaut doesn't really care what type of application you build. It is essentially anything with static void main can be built with Micronaut, and we have folks that are using it to build command line apps. We have folks that are using it to build swing apps. We have some folks that are using it to build mobile apps and so forth. So there's very a wide variety of use cases, because the core part of Micronaut is essentially a dependency injection and application level framework. And the way it works is that it uses the Java annotation processor API to hook into your Java C, so your compiler, your Java C compiler, and it computes everything framework related at compilation time. So what does that mean? So that means that instead of at runtime waiting for your application to be running and then dynamically loading all the classes in your application, figuring out all the methods that are annotated with at get or at post or at put, whatever, and configuring all that, Micronaut does all that work at compilation time. So by the time your application is running, there's not much left for Micronaut to do. It just starts up instantaneously. And it's really the result of a lot of lessons learned building Spring and Grails. I worked at with the Spring team for a long time and on Grails, and fought these issues on a daily basis. And I wanted to build something that would basically solve all these problems that we faced with user applications over the years. So we like to think of Micronaut as build time framework infrastructure. That may be a confusing term for an end user, but essentially, if you think about how a modern framework like Spring or CPI or Java works, you have features like dependency injection, configuration injection, support for reading annotations, support for serializing and deserializing objects by the Java Bean API or specification, and but it does all of these things in a completely reflection, runtime proxy, and dynamic class loader free manner. So when you run your application at runtime, Micronaut doesn't use any reflection. It doesn't generate any runtime proxies. It doesn't generate any runtime bytecode. And it uses just the system class loader, which dramatically reduces complexity at runtime of your application. Your application is a lot simpler at runtime, now potentially more complex at compilation time, but that price that you pay during compilation reaps big benefits at runtime. So with Micronaut, you can build a variety of things. Like I said, you can build microservices, you can build serverless applications, you can deploy Micronaut to AWS Lambda, to Oracle Function, to Google Cloud Function, etc. We have various ways to do that. You can build message-driven applications with the various messaging systems that Micronaut supports, from Kafka to Rabbit to more recently MQTT and so forth. And you can build command line applications. In fact, Micronaut itself has a command line called MN, to create applications. And the MN command line is written in Micronaut itself, computed into a native image, and delivered to the user. So kind of using Micronaut itself to build its own command line. And you can even use it in Android. You can use it in mobile, anything with static void main. And we currently support 3 languages: Java, Kotlin, and Groovy. So since Micronaut's been announced in 2018, it's had a significant impact on the industry and how framework design has evolved. You have on the Java side, you have folks like from Red Hat coming up with Quarkus, which based on similar concepts to Micronaut, build time, production of your framework infrastructure. You have the focus on improvements in performance in order to match Micronaut's performance from the Spring team. And even outside of Java, the .NET community introduced support for a equivalent to annotation processing in .NET, and a lot of those principles from Micronaut are being included in ASP.NET Core. And so Micronaut is really changing the face and the perception of server-side Java, and has done and made a significant impact over the last couple of years. And then we have GraalVM. So GraalVM, we actually, when we started building Micronaut, wasn't even aware of these. We weren't even aware of the existence of GraalVM. But when it came out, one of the features to make the biggest impact in terms of GraalVM was the support for computing native self-contained binaries. In addition, called native image. In addition to that, GraalVM offers so many other things, like it offers a JIT mode, which can increase your application throughput significantly and reduce latency. It offers the Truffle language framework, which allows you to seamlessly interoperate different languages, from Ruby to Python and so forth, Java, JavaScript, etc. And the feature I think that has attracted Micronaut users to GraalVM significantly is native image. And what it does is it takes your Java application, performs a closed world static analysis of your application, and produces a native binary for that platform. And as it happens, Micronaut and GraalVM were essentially a match made in heaven from the beginning, because in order to perform this analysis that GraalVM has to perform, it has to do a closed world static analysis. And that closed world static analysis works better if your application is completely statically accessible everywhere. If you use any kind of reflection or runtime proxy or bytecode generation or dynamic class loading, etc., all those things are supported by GraalVM native image, but you need to provide additional configuration to the native image tool to make it aware of those things. And since Micronaut doesn't do any of those things, it just kind of worked out of the box. It was like, wow, this is amazing. These two work wonderfully together. And the startup time and memory consumption impact of native image is pretty compelling. You get a drop down to 20 milliseconds in terms of startup time. I mean, Micronaut in JIT mode is no slouch. It'll start up in around 500-600 milliseconds. But dropping that all the way down to 20 milliseconds, and pretty much the memory consumption dropping from about 100 meg to 18 megabyte is a dramatic improvement. So GraalVM and the native image are very cool, and nicely integrated into Micronaut. And the way you get started with Micronaut is to go to launch.micronaut.io or start.micronaut.io. And this is a UI for generating Micronaut applications. And it's actually an interesting reference application. So do look in the slide. I have included a link to the source code for this application. It's an interesting reference application for Micronaut because the backend for Micronaut launch is written in Micronaut itself, and it is deployed completely serverless as a serverless backend, and the UI is, I believe it's React or something like that. But anyway, the backend is running Micronaut, computed into a native image, running in a serverless environment, and so on demand, executing as users use it. And it's a pretty awesome reference application. And the other thing is it shares the same code base as the Micronaut CLI. So in addition to deploying it to a serverless backend powered by native image, we take the same code base and we compute it for the different platforms, for Windows, for OS X, and for Linux, into a native command line executable. So from the same command, from the same code base, we produce a command line which you can run locally, offline, or if you ever get back on an airplane, for example, you can use it completely disconnected from the internet to create Micronaut applications and get productive. So with that, let's start doing some demo and doing some more exciting things, because there's only so many slides that one can take, I think. So let's do a demonstration of Micronaut and what it's like. So first of all, let me go to Micronaut.io. And if you go here, you'll see that there's a generate project link which you can click on. And from here, you can see the latest version of Micronaut or the snapshot version. And what you can do is you can select your favorite language, whether you're a Java developer, a Groovy developer, a Kotlin developer. You can select your favorite build tool, whether you like Gradle, Kotlin, DSL, or Maven. And you can select your preferred test framework. You can also click this features button, and from here you can add additional features that Micronaut supports. For example, if you want to build anything for AWS, you can get all the AWS features. If you want to build anything for Oracle Cloud or Oracle, you've got Cloud SDK or function, etc. Or if you want connectivity like JDBC, you can select the various JDBC features that you may want to choose. So I'm going to select data JDBC, and from there you can click the diff button if you want to see what the impact is of adding that particular feature. So I added the data JDBC feature, and you can see that all it does is add a few additional dependencies, some other to the build.gradle, and add some additional configuration to the application.yaml. And if I were to switch to Maven, you'll also see that I can also produce a pom.xml for Maven aficionados if you prefer that to Gradle. Or I can choose Gradle and preview that, and you can see this is my Micronaut application. You can navigate in and see what's going to be generated when we generate my application. Once you're then ready to go, you can click the generate project button, and you then have the option to push this project directly to GitHub, which will do some auth with your GitHub account and then push the code into GitHub that you generate, or you can download the zip file. So this is the whole Micronaut launch UI for getting started. But in addition to that, we also have a command line interface. So you can see that I'm running MN version 2.2.3, which is the latest version of Micronaut. And you can also drop in here and interactively create your application locally, like I said, completely offline. Choose the features that we're interested in, for example, data JDBC, and enter, and that will create my application, which I can see into, and here it is. So maybe you can then open that in your favorite IDE and get set up pretty much instantaneously. So let me enter into presentation mode in here. So okay, so this is a Micronaut application, and you can see that you have a application class which allows you to run your application locally. So I can just right click on this, for example, or if you're a keyboard fanatic, you can do it via the keyboard, and that will run my application locally. I can also come in and you can see I got a test generated, and the default test is using Micronaut test. So at Micronaut test, which is the test framework, which allows you to do things like dependency inject components into your test. And you can see that that's generated from me out of the box. And this test is just testing that the application starts up correctly. and you can run it inside your IDE, and you can see that that starts up and all is well. So that's how the basics of a Micronaut project. Other things that I can explain here is that we have some configurations. So there's an application.yaml. I chose the JDBC feature, so it sets up an in-memory database as well. In this example application, as you can see, you got logback for logging. If you're not a YAML fan, and I know there's a whole bunch of non-YAML people out there, you can also use application.properties if you prefer, or application.json, or I believe for Kotlin users, we also have HOCON support or config4k support. So there's a variety of configuration formats that are available, and of course, modern IDEs like IntelliJ and the upcoming VS Code support we have also have the ability to autocomplete all these properties. So I can say, configure my host or whatever, and that's all completed for you automatically and out of the box. Okay, so most applications start out with some kind of like Pojo entity model where you model like the entities or the domain in your application. And in generally with Micronaut, what you want to do with these types of classes is annotate them with app introspected. And the reason for this is because in traditional frameworks have often used what's called the Java Beans introspector. So it's this guy here. And the Java Beans introspector can be used to, introspect the bean properties of class and so forth, and get all its properties. I think you have to call get bean info or something to get a particular information about a bean and about its properties and so forth. And traditionally a lot of frameworks have used that, but it's based on reflection, and Micronaut is trying to avoid reflection. So for example, if I want to serialize this person class to JSON and back, or say to a database without using reflection, we have to let Micronaut know about that, and that's what you do there. So you can do things like make some properties there, and then generate a constructor for that. We add some getters and so forth. And what you can also do is Micronaut fully supports bean validation, so you can see things like not blank on the name to so we don't allow the name to be blank, and maybe people have to be 18 years of age, etc. So you can have these kind of dependency constraints directly here. And this is actually immediately emerges one of the problems I was telling you about is this not blank constraint with a traditional framework. Because of this is on a private field, you'd have to reflectively access the private field to retrieve the annotation, and again that breaks potential things like the module system and encapsulation and so forth. Accessing that private field when you really shouldn't be, just to figure out whether it's not blank. And the other problem is you might have the Java Beans spec allows you to declare constraints and so forth, both on the getter and on the field. So I've got a name field and a getter, and hopefully the upcoming support for records in the next release of Java is going to improve this matter. I think records will be used to model these kinds of classes a lot more frequently. But you can see that you can define annotations both on the getter and on the field, and obviously as a framework, Micronaut has to combine these two. And luckily we don't do that runtime, we do that at compilation time. So at runtime it's a lot simpler to analyze everything and so forth. So here we have my person class and so forth. So maybe you then define like a person service, I don't know, something like that. And maybe there's just like a method that lists all the people or something to that effect. And maybe we just return a list and person red, and another person, and so something to that effect, where we have some kind of component. So you're immediately wondering, I guess, if you've never done kind of DI before, what does this at singleton thing mean? Well, this is part of the Java inject specification, and it's one of the scopes that's available. So this is just saying that there should only ever be one instance of one of these services, in this case, person service. And I don't expect there to be any more. There should only be a single instance of it. So we're modeling that by saying this is at singleton. And the next thing you might want to do is write a web endpoint to expose all of this. So let's write a person controller. There it is. That allows me to map maybe to the people endpoint. And what you can do is just dependency inject directly the person service into my controller. Just add a constructor parameter. There it is. And so this is using constructor injection, and this is definitely the favored way, the Micronaut preferred way of doing things. So it is possible as well to get rid of this and instead use field injection using app inject like that. However, that's really, from my perspective, a little bit of an anti-button, because it's much easier to it's harder to see the kind of requirements of the class. If this is definitely required and it could be null, you would have to, you add risk of having null pointer exception as well. When the constructor argument approach, I think, is much cleaner. You know exactly what the class requires to function. In this case, this controller requires the person service to function, and of course you can add validation, things like non-null to that. So you expect that should never be null, and etc. So you can do things like that, which I think validating the constructor argument is a better approach. Okay, so we can add endpoint here. That's going to list my people and expose a kind of web endpoint for this, and we can return person service.list people. There we go, and there we go. So we've implemented some basic, pretty simple functionality to that we can model. So now, how do we write a test for this? So and you can write a test for the person controller, and like I said, we're going to use the Micronaut test annotation for JUnit5, and we're going to add a test here, and we can also in JUnit5 do things like use app inject to inject the person service or whatever, or the person controller if we wanted to. In fact, you can even use constructor injection in your tests as well if you want to keep that policy of using immutable types and so forth. But what I'm going to do is going to define a client, and Micronaut has a built-in declarative HTTP client. So what you can do is define the HTTP client like this, just on an interface. And you can even do things like just match the method signature. So there we go. So this is a client that's going to be used for the scope of this test, and we can inject that person client like so, and then we can add a test list people like so, and we can say set equals to person client dot list size for the moment. Replace that with static import and run the test. And if the demo guys are with me, everything should pass. So it just does pass, and that's good news from my perspective. So what a few important things to note here is that this is a full integration test, and in fact, it's even creating my data source and etc. And one of the things that really changes about the Micronaut experience when you're using Micronaut is integration tests pretty much run as fast as your unit tests. And so many frameworks out there have this extensive mocking on libraries or test libraries that you have to learn and understand because the framework itself starts so slow that you have to mock out parts of it in order to not have that problem. Micronaut is so fast that we have applications that have thousands of tests, and they run only a couple of minutes. The Micronaut test suite itself is testament to that, which runs very quickly and is primarily all integration tests. So you have this completely different experience, with tests executing instantaneously, and they're full integration tests. Now, if you don't believe me, we can come into the log configuration in here, and you can always enable HTTP logging. So I can say enable HTTP logging in my test, and then you'll see in my for my client, and then you'll see in my test output here, which is in here something. Why am I not seeing my test output? That's a good question. I don't know. I let Micronaut trace. That's weird. And okay, I don't know why I'm not seeing my test output. We'll have to figure that out. But anyway, so basically, this is right now this application is not doing anything particularly complicated. It's just using in-memory data structures and so forth. Let's take this a bit further and add some database-related functionality to this application. So one thing I'm going to do is I'm going to come into here and I'm going to get rid of that introspective and add mapped entity. And I'm going to make this a database entity. And the only other change I need to make in here is I'm going to add a private long ID and add generated values to the ID, and add the ability to set that. You can also potentially add the ID as a constructor argument, but in that case, one of the limitations of doing that approach is Micronaut data cannot send a new ID back without refreshing the instance. So that's one thing to keep in mind. So what mapped entity does, it says I'm gonna assume that this entity maps to a database table called person, and that each property maps to a column in the database. And the next thing you can do is I can, for example, modify this person service to instead be an interface that extends from CRUD repository, and I can provide it with the different with the entity name and the ID type. In this case, person, and the type of the ID is long. And then I can make this a JDBC repository instead, because I'm using the in-memory HTTP database. I'm just going to set the dialect specifically on there, and we can probably get rid of this like that. Now that's probably going to cause this to break, which it does, which we can replace with find all, which is one of the methods that you'll see that is available from the CRUD repository interface. So you can see there's save and update and save all and find all. Only thing is that find all returns an iterable by default, so I think probably we can change that to just using altering the return type in the overridden method. There we go. So now we have the database query going on. So how do you save data? So one of the things that you can do, and I think if I run this test now, I imagine it will probably fail because I don't have any data. So right, so I was expecting 2, but there's 0 records in the database. So so one of the things we can do is set up some data. So I'm going to do that by modifying my application class here, and I'm going to add an event listener that on an init method that listens for a startup event. And this guy is going to be transactional. So we're going to add some transaction management functionality to this event listener so that runs within the scope of a transaction. We can, in that sense, inject my person service into my application like that. And we can do things like stable, right? That's live new person Fred 25 and Bob or something like that. Something along those lines and so forth. So yeah, if we run that now, I imagine the test will pass, which it does. We're saving a couple of records in a transaction, and now we're back to 2. So that's how easy it is to work with Micronaut Data. And this is using Micronaut Data JDBC, which is a JDBC-based implementation. We also have support for JPA if you prefer JPA, but Micronaut Data JDBC allows you to be closer to the SQL and is much lighter weight. And you can see, as I said, even though I've got JDBC access, database logic access going on, I'm still able to execute tests very quickly. And I remember as well that we have also added those validation annotations and so forth. Those are, automatically picked up by Micronaut Data as well. So any kind of validation that you do by passing something blank or so forth would automatically be picked up. So now that we've done all this, how do we take our application into production? So there's a few ways you can do that. One way is you can assemble it up into a runnable jar like so. And in that case, we can just jar and run the fat jar, and that's it. My application is up and running, etc. And that's a pretty simple way to package up a runnable jar file if you're using JIT. And then the other option is with GraalVM native image. So I can do GraalW if I can type native image, and this will build my application into an appropriate native executable, packaging up everything it needs to package up, and essentially making a native executable out of my application. Now, this building a native executable in GraalVM is takes some time in that because it has to do this, like I said, closed world static analysis of the entire application, figuring out all the different reachable areas of your application and converting that into native code, storing some objects on image heap, initializing other objects at runtime. And the whole process can take a couple of minutes to complete. So, in general, with native images, you would generally build them as part of your CI/CD pipeline. I don't anticipate that a lot of people are going to be building native images every time they make a change to their application. And that's one of the reasons why it's so important that the framework that you use works consistently in both native and JIT modes. And we've gone to done extensive work to make sure that that's the case so that you can reliably run. And we also have a ability to run tests against the native image. You can do GraalW test native image, and it will run some of your tests against the native executable. So instead of starting an embedded server using Java, it will embed the native version of the application, and you can run your integration tests against the native version, which is nice. And so that you have this surety that your application works, which is pretty important. So you can see GraalVM goes through these various phases, producing the native image, and the last one is to produce the image itself. And once it's up and running, it's available in the build directory, in the native image build directory, and you can run it. And you can see that the application startup time with this application, which includes in-memory database and everything, is 31 milliseconds, which is significantly faster, which for serverless use cases is pretty outstanding. So that's the demo of Micronaut. So in a lot of cases, this example of some things that GraalVM native can bring to you. We have support in Micronaut for Oracle Function, as well as, like I said, AWS Lambda, both native and JIT mode, as well as things like Cloud Run and so forth. So we have support for a variety of different clouds, There's definite benefits if you're going the serverless path to using GraalVM native. This particular graph here, the blue box is the native image and the green one is the JVM on Oracle function. And as you can see, the cold start performance is significantly faster, which for certain types of applications, for example, if you look at Micronaut launch, Micronaut launch has a React UI and a serverless backend. So, the backend has to respond in a timely manner in order for that UI to remain responsive. So the cold start performance in that case is really important. And as you can see, this impact that native image has for serverless for Java applications is a significant boon for serverless architectures. The native version, for example, on our function starts in around 4 seconds, whilst the non-native version one is 40 something seconds. So Micronaut itself is super healthy and in active development and so forth, and it's being actively developed. And this is one of the important aspects of Micronaut in that we have a team at Rocher Labs working on Micronaut, which I think we're up to 4 people now. And but there's also engineers from object computing from Google as well contributing to it on a regular basis. And so forth, and that helps in terms of its diversity and ability to support different clouds, different environments, and that kind of vendor neutrality in a way, and different projects. So do start the repository as well that shows your support, Micronaut project / Micronaut core. Do star us and keep an eye on it, because the project keeps growing and keeps getting better. So then, in summary, Micronaut and GraalVM are leading this AOT revolution to moving more and more processing to compilation time and using ahead of time compilation to produce native binaries from bytecode. And as you can see through frameworks like Micronaut, server-side Java is definitely adapting to the needs of the serverless world. And if you make the right framework choices, you can build more efficient applications today. We've had cases where people have halved their memory consumption even in JIT mode without GraalVM with Micronaut compared to other frameworks, just because of the memory efficient. From whether you go in the JIT mode with all those efficiencies that we put in place, or whether you go AOT and native, your application is going to be more efficient. And yes, AOT does sacrifice compilation speed, but it also enables, GraalVM is enabling types of applications that just were not possible before without GraalVM native image. There's some really interesting projects going on around things like a project from Gluon that are getting Java operational on iOS to the ability to run Java applications in IoT devices or devices with significantly lower memory availability. So and going native now is a reality with GraalVM. So some resources, we have a Gitter community, you can come chat to us, gitter.im/Micronaut framework. We have a great user guide and documentation, Micronaut launch, which I showed you, a great set of guides. You can follow us on Twitter. And like I said, do star us on GitHub as well. So that may be time for some Q&A. If anybody is available for Q&A, or if we have any questions.
I have a few questions that were recorded during the session. If you'd like, I can ask them.
Go for it, yeah.
So, one of the questions was, are there any plans for Micronaut to support Eclipse microprofile, which would allow runtime interoperability using the same development model with other microprofile implementations?
So yes, I'm currently participating. So the primary I think, microprofile includes CDI, and CDI, is one of the. We were very cautious with Micronaut about supporting CDI because there's cases that require runtime bytecode generation and reflection with CDI. So we didn't want to base Micronaut on CDI because when we came up with it, because we knew we couldn't be spec compliant. As it happens, Red Hat that came with Quarkus is not spec compliant either. So both frameworks realizing this, we have started an effort to standardize to a variation of CDI called CDI Lite. And the intention is that for both Micronaut and Quarkus to support that. And I imagine at the same time, we will look at microprofile support, possibly through the Helidon project as well, which will hopefully long-term rebase itself on Micronaut's CDI compliant implementation of CDI Lite. So that's the long-term plan, but there's still a long way to go, essentially.
Sounds great. Thank you. The question was, what does Micronaut provide additionally over Spring Boot? And someone in the chat had mentioned that it offers the reflection-free runtime, which is perfectly suitable for cloud deployments. Is there anything else you'd like to add to that?
Yeah, I think that there's aspects that Micronaut offers that Spring doesn't offer, for sure. One of the things is because we do everything at compilation time, we're able to provide a certain amount of checking. I didn't demo that, but for example, if I can add to this repository a finder like person find by name, etc. And that will work essentially. It will compile fine, etc. But if I were to make a typo in my code, for example, I misspelled something, you can see the IDE is already highlighting it, but you also get a compilation error from Micronaut. So we can do things in terms of providing a better user experience by hooking directly into your compiler, telling you where things go wrong. And because Spring is completely runtime based, that's not possible today. And that's a real nicety of being participant in the compilation process. And the other thing is, Spring has extensively large stack traces compared to Micronaut because Spring is based on reflection and runtime proxy generation, and that also impacts the debugging experience. So when you're working with Micronaut, it's typically easier to debug things because stack traces are much shorter. You don't get these monsters that is commonplace with Spring. To the point where they actually started editing out the stack traces in their error messages in Spring Boot because they got so big. So that's again something we wanted to avoid, and yes, the reflection-free architecture and so forth is important, as mentioned.
Perfect, thank you. We had a similar question regarding Quarkus. Is there a difference between Micronaut and Quarkus that you would like to highlight?
So that difference that I mentioned regarding Spring and this error message here also applies with Quarkus. So Micronaut and Quarkus are based on very different models. Quarkus does post-compilation bytecode enhancement. So you compile your app normally, and then Quarkus runs a secondary step that looks at the compiled bytecode and transforms and enhances it. This difference means that when they do their processing, they lose access to the source code. So producing these kinds of errors is not possible with Quarkus, or certainly not as easy as it is with Micronaut. So and the other thing is that in order to support that architecture, Quarkus needs extensive IDE plugins and for different IDEs and build tooling. For a very long time, we didn't even have any build tooling with Micronaut. We just used the default Gradle and Maven build processes because we're using standard, well-known Java annotation processing. So we hook into the Java compiler using the standard way. We don't do anything special, and we don't transform your bytecode. So that means that Red Hat has to build and maintain those additional IDE plugins, and Quarkus won't work in every single IDE without special plugins. And you have to rely on the build tooling a lot more, whilst in Micronaut you can just run standard Java C, and it works, right?
Sounds great. Thank you. Okay, another question was, is there compatibility with Project Lombok?
Yes, there is. Yes, we have. In fact, if you go to Micronaut.io and then you go to generate project, I believe we have, or I think it might be, yes, there it is. So you can choose Lombok, and it works with Micronaut. We had to actually do some special, basically in your build configuration, the Lombok processor has to run first because Lombok transforms the AST of Java, and Micronaut needs to see that transformed AST. So the Lombok processor has to be first, but this, by choosing this, it'll show you exactly how to configure Lombok and set it up. And click preview here. You'll see it's just an annotation processor declaration, and it works fine. Yeah.
Perfect. That's very nice. So also, is a long compile time a pain point during development, or is there a separate hot deploy mode?
So yeah, there is a hot deploy mode. The long compile time is not. The other big difference that I forgot to highlight regarding Quarkus and Micronaut is Micronaut supports incremental annotation processing, so incremental compilation. So in general, when you're in development, you don't really notice the difference because everything is incrementally compiled. But we do have, when I do small changes here, I'm not recompiling all the code. It's essentially only recompiling a subset, which is very nice. But we do also have support for, so I can do stuff like GraalVM run/t, and we also have a Maven plugin which has the same feature. I think I already have the server running. That's why it didn't let me do that. But basically, I can do GraalVM run/t, and the Maven plugin has the same. And you can see it starts up, etc. And if I come in here and make some change or whatever, and say that, you'll see that the server automatically restarts and refreshes and so forth, and automatically for you, and you can go back to your browser and check changes and have those automatically refreshed.
Nice. Okay, thank you. So I'm looking through to see if there are any other questions here in the comments. Looks like there is a little bit of conversation. People are interested in using Micronaut. That's for certain.
That's good news. That's a good sign.
Indeed. Okay. Well, I'm not seeing any other questions. Anything else out there?
Well, if anybody does have a question, do remember that we're on Gitter. I'm on Twitter as well. You got all the social links. Just send me, at me or ping me or whatever, and I'll be happy to answer questions afterwards. If you have any other questions that come to mind after the talk.
Sounds great. Well, we definitely appreciate having Graeme Rocher here to introduce us to Micronaut. This has been an excellent presentation. We appreciate everyone's attendance, and there is another presentation starting here in just a moment. Emily Zhang, and her session is called Easy Peasy Cloud Native Microservice Development with MicroProfile. Thanks again, Graeme. We appreciate it.
Thanks a lot.
Take care.